All stars that shine in the night sky revolve around a center of mass. These stars would always be tending to resumate their state of rest and immobility, which, however, could not be achieved. This problem of relative and continuous motion would be related only to those who observe the stars. To do so, the observer would depend on time and, therefore, on his memory. As its light has a fixed speed and is limited to 300,000 kilometers per second, when the star was sighted, the observer would already be looking continuously at his own past. If the stars reach their own resting positions, space would become flat, which would violate the uncertainty principle. Thus, it is concluded that the continuous and relative movement in our universe would preserve the functioning of our memory. So, even if the universe was stationary at its origin, it would only exist for us as long as it assumed motion. This movement would only make sense in our past, or when space already presented itself to the observer, plus the one dimension of time. Science postulates that, before the beginning of time, everything would have been on the center, or on an extremely dense point, smaller than the eye of a needle. The description of the center is compatible with the resting state of space, which could not be reached by the stars. So, what you see in the night sky would be the unfolding, the virtual exposure of that isolated point in 3 dimensions, through the light that emanates from it. This abrupt exposure would occur when time was added to the other 2 dimensions of space, which are width and length. In the resting position of space, or at the center, there would be no motion and no forces acting. There, the light would be everywhere. Thus, there could be no real separation between the energetic extremes of visible light, as would be the case with ultraviolet and infrared. This polarization of light, where all bands of the spectrum would start from the same moment in time, would have been exposed to the observer in the celestial dome in an abrupt way. This would have happened in the exactly moment after the Big Bang. So, all the stars that we can observe with a delay in time would continue to occupy the same center that they occupied before the Big Bang. What would have changed would be just the exposition of this point in 3 dimensions from our point of view. It would have placed each of us on our own center from which we look outside of ourselves. Each of us would have our own time frame 0. According to the thought of Giordano Bruno, the philosopher burned at the stake of the Inquisition, because of his revolutionary ideas, the center of the universe would be where an observer was. The periphery, in turn, would be nowhere. Unlike the observer, and despite occupying their own centers, the stars would have no way of knowing this. The impossibility of any star reaching its center of gravity or its state of rest would cause its movement in the night sky to become cyclic. Due to the torque, the star would rotate eternally around the center of mass. The energetic leveling of starlight, related only to our point of view, would fit this movement in the description of circular and uniform. That is, the motion of any star in spacetime should be relative only, occurring with constant velocity and acceleration. As time could only be evaluated and measured in our past, since the future has not yet happened, this time would remain eternally indexed to the continuous curvature of space. when described by light, this curvature, even if it were real, would be virtually annulled by the polarization to which the radiation would have been subjected, and which would have occurred when light still occupied that centralized point, smaller than the eye of a needle. Therefore, when described by light, the possible fictitious force related to the formation of the curvature of space would have to have a negative orientation capable of contracting time until the moment of the Big Bang. Thus, because light said to us that the curvature of space would be negative, it could not be directly measured, nor could we assess its possible influence on the density of stellar masses. To know about the existence of stars, the observer became dependent on cosmic radiation. As it would have been leveled at its energetic extremes, without any direct record, the radiation shows us each star acting in the form of an incandescent lamp of regular and continuous brightness. Thus, the brightness of each one of them should decay due to the increase in the distances at which they were placed. Without light, the space, then placed outside what can be observed directly, could be influencing the mass density of a star in a totally veiled way. This would have important ramifications. For example, you look at the sky during the day and see the sun walking along the ecliptic in uniform and circular motion. If space were influencing the sun's density over time, concentrating or diluting its mass, this could not be communicated to us by the light our star emits. The event of mass density variation in space-time would be hidden by the complementary contraction of time during the formation of the negative curvature of space. That is, space would temporarily retain time in its expansionary phase. It is understood why the energy of the vacuum should be negative, as it is verified at the atomic level in the Casimir effect. All the different levels of matter would obey the same principle of delayed observation. That is, to see an electron or a star, it is necessary for the light to be scattered locally. Thus, the instantaneity of the observation would also have to be valid for the macrostructure of the universe. As already mentioned, space would retain light when it negatively curved. From the point of view of those observing from Earth, the impression would remain that the light, before reaching him, would have transited his future. In the case of Beta Andromeda, light from the star would need 75 years to reach Earth. When space curved in the future, it would contract time to subliminal levels, or levels that could not be directly measured by our experimental methods. Space would concentrate the star's mass as it stretched, making it denser. However, when we observed the star in our past, using its light, we could not notice any appreciable change in its mass or volume. In its densest phase, the star would be expected to shine less than normal, or to emit less light and heat into space. If the space curved less from the outside, this could be interpreted as a contracting movement when seen from the inside. In this case, the opposite would happen. The star would lose density and increase in volume, emitting more light into space. If there were another star nearby, it would move away due to the relaxation of tension in space. With this, one can think that the stars really pulsate in the night sky, because the veiled variation of their densities would be expressed in their variable brightness. The importance of the veiled action of space on stellar masses lies in the way it would manage time in our daily lives, as well as the relative movement of the stars, which we observe in the celestial vault. Another curiosity is that being negative, the curvature of space would be placed outside the observable space-time. Thus, there would be no need to count on any absolute movement between the stars when they are evaluated with a delay. When moving away or approaching each other, the stars would not abandon their original positions. Although relative motion in space-time remains dependent on the stretching of space outside of it, observable motion would be time-restricted. It is that, due to the complementary contraction of time in the expansionary phase, space would have become a phantom entity. When we looked in the direction of the celestial ball, or in a sense of our past, we would see the delayed projection of the polarization of the cosmic radiation. Since this polarization could only be registered with a delay, microwave radiation came to be called background. To our point of view, ultraviolet and infrared appear separate from each other, one-tracked, and occupying opposite ends of the spectrum. By the time the pontiform center unfolds in 3 dimensions, in the post-Big Bang, there would already have been an inversion of the arrow of time, and light should appear depolarizing. At the time, the space should have already entered its contraction phase. This phase would be characterized by a continuous drop in elastic potential energy within space-time. If our universe were currently in its expansionary phase, this dip should not be expected. It's just that, when space expands or curves, the resulting force would point in the opposite direction, with an increase in potential energy. When we recorded the delayed projection of light polarization, which we used as support for the Doppler effect, the radiation itself would exclude the direct recording of the space contraction phase, which should have been occurring in real time. That is, the depolarization phase of the light would be excluded by its own polarization phase, recorded in a time-phased manner.